As scientists, we know that every measurement involves uncertainty. A quantitative measurement involves a number which is reported with the appropriate number of significant figures. The last significant figure is the uncertain digit. That's where the error is. In this video, we'll look at how the error in a measurement is reflected in calculations involving that measurement. So here's how we round numbers in a calculation to reflect the uncertainty in a measurement. In a calculation that involves addition and subtraction, look at the number of decimal places. For example, this number has 2 decimal places, this other number has 1 decimal place, so the sum will be rounded to 1 decimal place. For a calculation that involves multiplication or division, look at the number of significant figures. For example, this number has 4 significant figures, this other number has 2 significant figures, so when we divide one by the other, our answer should be rounded to 2 significant figures. Let's practice. Stop the video and fill in these blanks. Here are the answers. We know that density is mass divided by volume, so the mass has 3 significant figures, volume has 2 significant figures, so our answer for density should have 2 significant figures. The mass of water is found by taking the mass of the beaker plus water minus the mass of the beaker. We have to subtract, so look at the number of decimal places. Next, we have to divide the mass of water by the volume of water. This number has 3 significant figures, the volume has 3 significant figures, so our density should have 3 significant figures. So you're interviewing for a science job and you're asked to demonstrate your knowledge. Stop the video and answer these questions. Here are the answers. Let's do C first. Mass is reported at 2 decimal places. That means the uncertainty is in the hundredths place. The uncertainty in mass using a triple beam balance or pan balance is in the hundredths place, so we actually cannot tell which measuring device is used. For D, note that the volume of water has 1 decimal place. That means the uncertainty is in the tenths place. That means the digit we know with certainty is the ones place. That tells us each line is 1 milliliter. That means a 50 ml graduated cylinder was used because each line on the graduated cylinder is 1 milliliter. For E, to get better results, use measuring device which has smaller uncertainties. A 10 ml transfer pipette has a smaller volume uncertainty than a 50 ml graduated cylinder, so that probably would have given better results. For question A, we need to know the mass of water and the volume of water to calculate the density. So the mass of water is 9.75 grams, the volume of water is 10.0 mils. That means the density is 0.975 grams per milliliter, using significant figures. Percent error tells us how close we got to the true value. So the true density of water is 0.9974 grams per milliliter. Our experimental density is 0.975 grams per milliliter, so our percent error is 2.2%. Note that when you subtract, you round to 3 decimal places, but that third decimal place only has 2 significant figures. And then when you divide, you have 2 significant figures in the numerator, 4 in the denominator, so our answer should have 2 significant figures. The other important thing is note that this number is an intermediate calculation, so do not round that number until you get to your final answer. So let's talk about conversions. To convert from one quantity to another quantity, we need to use a conversion factor. For example, to convert A to B, we need our B to A conversion factor. Density is used as a conversion factor to convert from grams to mils or mils to grams. Make sure the units cancel out to give us the units we want. So let's practice. You're given the mass of a liquid and the density, convert mass to volume. And the answer is, here's another way. Good work. Here you have a cup of a liquid and you know its density. Stop the video and answer these 2 questions. And the answer to A is no, because water has a density of 1 gram per milliliter, which does not match the density of the liquid 0.79 grams per mil. For part B, note that density is the conversion factor, and using dimensional analysis, milliliters cancels out, leaving us with grams. Let's practice a few more conversions using dimensional analysis. If you've ever had acid indigestion, you may have taken Tums, which contains calcium carbonate as its active ingredient. Or maybe you took Tums as a calcium supplement. So let's convert from mass of calcium carbonate to mass of calcium. Here are the conversions. So first we convert from milligrams to grams. Then we use the molar mass of calcium carbonate to convert from grams of calcium carbonate to moles of calcium carbonate. Then we convert from moles of calcium carbonate to moles of calcium because in 1 mole of calcium carbonate, there's 1 mole of calcium. And finally, we use the molar mass of calcium to convert from moles of calcium to grams of calcium. And the final answer is 0.22 grams of calcium. So stop the video and do this question. And the answer is, many of the calculations we do in chemistry are conversions, so practice the dimensional analysis. As future scientists, engineers, or medical professionals, you'll be making measurements or looking at numbers that were measured by someone else. So stop the video and review how we look at error and uncertainty.